Hey, so I'm going to add to the ResNet 18 full implementation video. Um, I'm just to make it one cohesive unit. I want to add in batch norm implementation, like I said I would, and then you know deploy it to Runpod. Um, actually, I'll just add the batch norm implementation, and then I'll deploy it to Runpod in a separate video because I think it's already long enough. But let me add into the batch norm implementation right now. So here we have our NN modules. Um, okay. So self. So what BatchNorm does is you essentially normalize per feature channel. So for every sample in your batch, for that specific feature, for the height and width, you average across every sample in the batch, and then the height and width for that specific channel. You'll see what I mean. So num features. So the number of feature maps, the number of channels. EBS. This is a small numerical value you're going to add to your the calculation of your estimator in order to um, prevent division by zero, or to prevent numerical instability um, by having numbers that are really, really close to zero, because that requires extremely high precision, um, um, which can lead to numerical instability. Momentum. So we are going to, again, this is a simple educational sort of implementation of batch norm. And all of these implementations over time are going to make better and better and more optimal, right? Like as we continue to learn. Um, but momentum is a way to, during evaluation, so you're going to learn parameters of this batch norm during training, and then during evaluation you're going to apply these learnable scales and shifts, and but you're going to weight the the historical data more, the historical learnings more important than whatever the current batch. You're gonna weight the previously accumulated mean and variances to be more important than the current mean and variance. By well, how you weight the importance is going to depend on this number right here, but zero point 0.1 is the default value because you want to weight your historical learnings as being more important, and you'll see what I mean. So Actually, let me just rename this file so folks don't get confused. But so it's just, I did make a few changes, but it's not relevant for the portion of this video right now what changes I made. I'll go over them slightly, but essentially I just substituted in this, I'm going to substitute in this new batch norm, but I'm just going to keep the file name the same so folks don't get confused. So self dot, what am I going to track here? Right, so this is this batch norm. The learnable parameters are going to be a mean, um, are going to be a scale and a scale and a shift. So like a mean and a variance. Um, they're called an affine. It's the fancy name is an affine transform, but it's just um, multiplying a variable by a matrix and then adding a bias. And the gamma is going to be initialized to, this is your scale. Um, this is going to be initialized to torch dot ones so that the initial parameters don't actually change the value. Don't So the initial parameters don't actually scale. So the initial scale doesn't actually scale. We want the model to learn the scale at first. So we don't. We want the initial parameters to sort of be an identity function. Um, Torch.1's num features. Oh, what just happened? Oh, is caps lock on? Wait, what is going on? I just deleted all that? Okay, huh. Let's, okay, momentum, gamma equals, and then your shift, right? So it's going to be an x, so it's going to be x times gamma plus beta, right? This is your gamma scale, so we initialize it to 1, so it's sort of an identity when you multiply it by x. And then the betas are going to be initialized to 0, so it's also an identity preserving operation upon initialization. And then as a register buffer, we're going to track the running mean. So we're going to have this accumulated mean that we track over time, and it's going to be initialized to torch.zeros. And this will all make sense once the code is sort of complete. You'll see. So let's see. I always have to implement batch norm backwards because I don't know why this one always just kind of, it's a little bit more difficult for me to conceptualize for some reason. But so, so basically what happens is when you send a batch through this layer, you're going to normalize each channel. So we'll say X hat. I'll start with the sort of final product, which is the value we're going to output. output, right? So we're gonna say um, x minus, right? So x minus mu divided by the square root of the variance plus your EPS value to prevent division by zero, right? So mu, so x minus mean, which is going to be a broadcast variable actually, which you'll see. And I'll just sort of put this in a register, a vim register, divided by torch dot square root of variance plus EPS. And just to make sure everything stays on one line, I'm gonna remove the self. Right, so I still have the camera, I'm leaning forward. So and then x hat, now we're gonna scale it and shift it, apply the affine transformation. So x hat times self dot gamma, and again this is, we're going to broadcast this, plus self dot beta. Okay, so that's what we're going to return. Now there are two modes. There's going to be the training mode and the evaluation mode. Evaluation mode is just going to use the statistics, the running statistics that we've calculated. Running mean, the mean is going to be the running mean, and the running variance. In training, now during training, we're going to learn the appropriate affine transformation. So the reason why the affine transformation is important is because this is what helps prevent internal covariate shift. This is sort of kind of the whole point of batch normalization, which is to prevent not only internal covariate shift between batches, so like batches, but also prevent internal covariate shift between layers of your resonant, right? So what that means is, and this is all to prevent numerical or training instability, right? So like remember, ResNet in general, with these networks that become very, very deep, we sort of want to make sure that the the magnitude of the parameters don't shift too much between layers. Like if we have this really deep network and the magnitude, right, like the average magnitude of the parameters of your, right, shifts a lot, like between layers, it makes it really challenging. It makes it challenging for the network to um, um, back propagate gradients sort of smoothly through the network, right? Um, we want gradients to sort of flow smoothly through the network, and the more the average sort of norm of the parameters lines up across these layers, the more smoothly the gradient can flow through the network. It's kind of a rough description. It's sort of the way I think of it, right? And then also, not only do we want to prevent covariate shift between layers, we also want to prevent covariate shift between batches. So each batch is like we can think of each batch as like a sample of the overall data, and if it's possible that different batches well different it's possible that different batches can have significantly different means and variances, right? And like, let's just take the extreme case where a lot of your batches have significantly different means and variances. That's also going to prevent uh, training instability. So having the network learn parameters, we want the network to learn an affine transformation, learn a scale and a shift, right? So learn a distribution for a batch that's robust to um, not only different batches for that one layer, but also sort of learns how to calibrate the distributions between the layers, right? Um, yeah, think about that. Think about that. Again, these are challenging concepts. These are very challenging concepts but these intuitions, man, these intuitions are like key. I'm telling you, as someone who started as a novice, started like, I still find this stuff really challenging, but these intuitions, like how you think about and visualize these uh the feel of these different operations and these different modules makes all the difference. This is where we want to get, because I still need to improve my learnings and grow my intuition and start to think about these problems in the sort of masterful way, right? So anyways, enough about this affine transformation. So during training, we're going to, okay, so let's calculate the mean. It's x dot mean, right? And the mean is across during training. So actually, I don't need this comment. Let's just continue. So the mean is across, right? So remember, x dot shape is always batch your number of features, right? Your channels, number of channels, height, width, right? So we're normalizing each feature map. So that means we're going to calculate the mean across all samples, all across the entire height dimension, across the entire width dimension. And we're going to do the same for variance. But this unbiased, now we need to add this unbiased. So there's this unbiased parameter on the variance calculation, and unbiased false means we're using n to calculate the population variance. And I think so it's like called like Bessel's correction. Bessel's correction. Right. So even though technically a batch is a sample, we're considering the batch to be the population. So we don't want to use Bessel's correction, which is n minus one for a sample variance. We want to use n for the population variance, right? So unbiased is false. And now, yeah, actually, this is a good educational implementation right here. There's so much content in these implementations. It's machine learning. It's a lot. It's a lot. It really is a lot. So, anyways, let me just type this out and then see if I can explain it after the fact. So self dot running mean. So I usually do it like this, and then I'll correct it. So m is self dot momentum. I'm just gonna make this this variable m, just to make sure this all fits on one line because it's easier to read. So 1 minus m times self dot running mean. So remember, by default, m is 0.1, so 1 minus m is 0.9. So let me type this out, plus m times mean. So what this means is 0.9 times the running mean plus 0.1 times the mean. So we're upweighting the value of the historical mean, right, of the historical accumulation of the historical mean that we've accumulated, and we're downweighting the importance of the current mean, right? So we can see that that stabilizes things if we choose momentum to be 0.1, because if we upweight the importance of the current current batch's mean, then we can see how it would fluctuate potentially a lot more, right? So we're mitigating the potential for that fluctuation by using momentum, right? In general, that's what momentum does. Is it it provides a potential mitigation for instability. Um, and then actually, this needs to be copied because running mean and running variance are register buffers. And their register and wait, did I do this? Right, this is correct, right. So running mean and running variance are register buffers to ensure that the model doesn't track them as parameters, right? And then we use torch.nograd to also further ensure that the model doesn't include the tracking of running mean and running variance in it doesn't include it in the computation graph, right? So the whole strength of PyTorch is that in order to backpropagate gradients, it creates this directed graph that links parameters to each other so that it can automatically calculate. It knows how, it has like very sophisticated algorithms to automatically calculate chain rule, right? So if you think about the chain rule, like for each parameter, for each layer of the network, you have to sort of chain your way in this calculation of the derivative through each of these layers. And the PyTorch's computation graph creates a directed graph that allows it to more easily calculate these chain rules. And when we say no grad, we're basically telling PyTorch that we don't want it to store the running mean and the running variance. We don't want it to consider it in its computation graph, right? And we also use copy towards that end, or dot copy towards that end. Okay, so yeah, this is why I always have to do batch norm, sort of work my way backwards, because there's a lot to consider here. I think this is it. So we have our parameter, ones for the gamma, zeros One's for the gamma, which is the scale, so it's identity preserving across upon initialization. Same for beta. Then we make sure that running mean and running variance are register buffers. Training. So by the way, self.training is a property of the parent class module, and it's going to be automatically switched to true or false depending on when we do so model.train. Right, model.train sets that boolean to be true or false. And then we calculate, so we have batch C, which is number of features, height and width. So we average across batch, height, width, right? So let's just see if we can find an image of maybe convolution operation. Once I have my iPad, I promise, guys, I know I keep saying this, it'll be much, much better. So I need a block diagram. So, right. So for these feature maps, if you can see where my pointer is, like let's say this is the output of one layer. And then imagine our batch size was 20. We would have 20 of these stacked, boom, 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 boom. For this is height and width for this square. For, we're normalizing across each element in the batch and all height and width. So we're basically taking the average just for that feature map. We're calculating the mean and the variance for that feature map, and then we're doing that for each feature in our input. And then we calculate the running mean and variance using momentum to upweight the importance of the historical data, of the historical of the aggregations, of the historical aggregations. And then if it's not training, right? So we calculate this during training. If the model is set to eval, right, we're just going to use the running mean and the running variance that we've, like all the learnings. We're going to use all the learnings that we've accumulated. And then x hat, right? So we're going to do your standard x minus mu. To calculate your estimator, you're doing your standard x minus mu divided by, to calculate your x hat, you're going to do x minus mu divided by the square root, and then we add this EPS just to make sure that there's no numerical instability. So just in case, so we don't divide by 0 in case the variance is really small, or to make sure that just in case the variance is 0, or if the variance is really, really small, then if the variance is really, really small and your computer has to be extremely precise, that can also cause numerical instability with your floating point operations. And then once we calculate x hat, we apply the learnable transformation so that we can mitigate covariate shift between batches and covariate shift across layers as much as possible. And then we return x hat. Phew. Okay, now let's see if this actually freaking works. So ResNet 18. This is going to be my new file, right? Because I did do small sample. So I added this do small sample just to sample the data set like really, really small just for testing. And I set it to true, but it should be fine because we're using the MNIST data, and we should see the validation accuracy increase within like 3 to 4 epochs, like to be pretty, pretty high. And then basically search BatchNorm. Right. I went from the original line that we had, which is NN, right? NN is our import from Torch. It's our Torch default import. Import Torch as NN, right? So we're gonna remove that. Basically, for each batch norm, I did our import, which is NNM, our um, custom batch norm implementation. Then I can just hit next and just search through this whole file, make sure they're all, which they are. So, and then you can see this config.do small sample that I added. Let's run it. Let's see if there are any issues. Python resnet 18.py. Fingers crossed. There probably are issues, of course. Did I not call super? I did not. Super dot init. Oh, right. Equals. Let's look at this one more time. Mean, variance. Mean is this. Mean, variance. Beta, gamma. Yeah, gamma. Running mean should be 0, so it's the running mean should be 0, so it's the identity. Beta should be so this should be gamma should be 1, so it's the identity plus 0, and then you're running mean, so that when you're multiplying, right, so the register buffer, the running mean needs to be, I don't know if I explained this. I explained why this is 1s and 0s for the identity preserving operation upon initialization, but also for the register buffer running mean, we initialize running mean to be 0s, right? So it's 1s here, right? It's 1s here, but for the register buffer, it's 0s because we don't want the running mean to have an impact upon initialization again, right? In the calculation of this statistic right here. So this looks all correct. EPS not defined. Self.EPS, EPS, self.EPS. EPS is not defined. Oh, EPS receives self.EPS. Looking good so far. Still on the camera, yeah. Looking good. Yeah, this is looking good. This is looking good. The real test is going to be when we scale it up on CFAR 10, but yeah, there you go. Implemented batch norm. Hopefully this is fully correct. We'll know for sure when we scale it up, but I'm pretty sure this is correct. If not, we'll make any small adjustments that we need to.